Hey kiddos, welcome to our second video on equilibrium. Today we're going to talk a little bit about the introductory math behind equilibrium, and that's going to come in the form of equilibrium constants. So equilibrium constants all revolve around something called the law of mass action, and essentially what the law of mass action is it takes an equation, okay, so generic equation here, obviously that's nothing normal that we would see, and then it's going to arrange it in a way that relates the molarities, okay, the concentrations of each of the species, okay, so the reactants and the products, and it's going to relate them together into an equation where we can calculate our equilibrium constant. Now, usually we just denote that as a capital K. Sometimes we'll see it as a Kc, which will differentiate it from Kp, which we'll talk about a little bit later in the video, but generic K means Kc. It means concentrations. A couple of things you need to notice right away here are that it is in brackets, so that means the concentration is in molarity, that it's products over reactants, just like almost everything we've done this year has either been products minus reactants or products over reactants. So make sure you get that. And the other thing that makes it a little bit different is that unlike our kinetics equations, we actually pull the exponents here directly from the balanced equation. So in kinetics, we had to have some experimental data and sort of had to do some figuring to see what the rate law was and what the exponents were going to be. In equilibrium, that's not necessary. Whatever the balanced coefficients are, those become our exponents in our law of mass action. So that's a lot of stuff on one slide. What does that look like when we actually try to figure one out? So let's do that. Let's just write down what a law of mass action would be for this particular case. So again, it's K equals, and you can put Kc if you want. That's a K. I know that traditionally in Ks they connect together, but you know, close enough. So Kc, and we have products on top. So NO2 to the 4th power, okay, because that is our balance coefficient there. Water raised to the 6th power. Again, that's our balance coefficient. And all of that is going to be over our ammonia. Okay, that's to the 4th. And then oxygen to the 7th. Now, this looks a little weird for one thing, just because we're not used to dealing with a whole lot of exponents that are like 6th and 7th. And to be honest, you're probably even in chemistry not going to see a whole ton of those because we don't often see really high coefficients like that. Usually our balanced equations come out to be more like 3, 2, 5, stuff like that. But you'll occasionally get those. And that's a little bit worrisome when we do the actual math, when we do our ICE tables in our next video. But we'll see that we'll work some ways around that, because obviously if you had, say, an x minus 1 in here and had to multiply it or had to raise it to the 7th power, that would get real ugly real fast. So we'll find some ways to work around that. But this essentially is, if you're asked to write out your equilibrium expression, that's all this is. Okay, so Kc, products raised to their power, over reactants raised to their power. So pretty simple. So let's just work a quick math version of that just to make sure that we can plug in all the numbers right and get all of our calculations correct. So we're going to go back to our Haber process just because we're used to working with that particular equation. It's always good to have something familiar there when we're plugging these in. So our K value is going to be equal to our products, which are ammonia. Okay, sorry if you guys can hear my kids in the background. I assure you they're behind like 2 doors. Over N2, now N2 is to the 1st power because there's no coefficient there. Hydrogen raised to the 3rd power. Okay, so that's the actual expression. And then, of course, we actually have to plug numbers into that. So we're going to take our ammonia off the top, and I'm going to convert these out of scientific notation just because I think it's a little easier to plug into my calculator. You certainly do not have to do that. You can plug them right in that way and raise them to those powers, and there's nothing wrong with that. It's just the less time times 10 to stuff that I have to write here, the better the reading is for everyone. So that means, and then I totally go against that and don't do what I said I was going to do. So that means that this bottom one then is going to be 0.85 for the N2. Okay, again raised to raised to the 1 power. Okay, and then 0.00, and see, now you see why I tried to write as little as possible. Raised to the 3rd power. We're going to plug all that in, and then we are going to get a result once we punch that into our handy dandy calculator or look at the paper where we have previously worked it out, as the case may be. and we're going to get 37,950, and then some odd decimals that I'm really not going to worry about. And technically speaking, obviously, you would probably want to round that to, you know, some significant figures to make it a little bit more accurate, since everything in my original had 2 sig figs. Then that makes it pretty safe to assume that I've got 2 sig figs in my final answer. And so that would be it. You'll notice that I've got no units on this, and you shouldn't have any units on this. We don't carry any units on equilibrium constants, okay? So you won't get a question like you did in kinetics that says, hey, what's the units for K? You're not going to have any of those. There aren't any units for K in these things. Okay, so pretty straightforward. I mean, as far as math goes, that's not too bad. It's just a matter of remembering products over reactants. And then the part that always messes people up, in my past experience, is that you have to remember to actually raise things to the power. So when you plug it into your calculator, you got to remember that when you put this 0.0031 in, that you've got to cube it, okay? Or that if you're in the previous one, that you had to raise it to the 7th, or whatever you have to do. And if you're having problems punching those into your calculator, as usual, you know, come by, ask. I'll make sure that we can figure out what you're plugging in right or plugging in wrong that might need correcting. So sometimes what we'll have is we'll have a situation where we actually need to take our K value then and manipulate it in some way. And so, like for instance, maybe instead of the original equation, maybe we're working an equation where it's like, say, half of that. So instead of an N2, it's a half of that. Then it's 3 halves. Okay, divided by 2, which would obviously make that 1. Okay, so what do we do then? Well, we have to plug everything back into the law of mass action and use different exponents, and you could do that, and that would be perfectly valid. But what's actually easier, and since we're looking for ease and quickness, say on an AP test where you get a bunch of multiple choice questions, the easier thing is just take your original K value and raise it to the power of whatever your new coefficient is. So if we took our 38,000 there, we would raise it to the half power, okay, or 0.5. And we would get, let's see here, about 195 or so. You're actually going to get a little different than that because I used the unrounded to sig figs number when I calculated that, so forgive me. So that's pretty simple. And then if we had the reverse reaction, again, we could plug it back into the law of mass action, but with this stuff on top and then this on the bottom, raise it all to the same power. But really, we can just take the reciprocal of K, and so that means you could just take your, you know, take your 38,000, okay, and then in your calculator, just take your reciprocal key, okay, your x to the -1 key, and then in this case, we would get 2. If it looks like I'm looking at my cheat sheet, it's because I am, because I worked out all the calculations ahead of time, because the last thing you need is for me to take 5 minutes fumbling around in the calculator. So that is 10 to the -5th. Yeah, I know. Okay, so those are pretty simple. So if you got it reversed, you take the reciprocal. If you got it, if the coefficients are multiplied by some power, you just raise it to that power. Okay, pretty simple, easy way to manipulate K. So a couple of quick hit points about these equilibrium constants. Even though at a given temperature, K is always the same, the concentrations might be different. So if you're working on a certain reaction at a certain temperature, the K value is going to be the same, and we can then shift the concentrations around. In fact, that's most of what we're going to do in the next video, is talk about, I know this concentration, but I don't know the other two. How do I figure them out? Okay, we're going to be able to calculate that stuff. If we know all of the concentrations, then we would say that that is the equilibrium position. So concentration of N2 is this, and concentration of H2 is this, concentration of NH3 is this. That is our equilibrium position. We know where it is. And then, much like we said that we were talking about, we could say that something favors the right or favors the left. We could also say if we know our K values, if K is above 1, then the equilibrium position is to the right, meaning that it's going to favor products. Okay, and if it's below 1, then it's going to favor the left-hand side, meaning it's going to favor reactants. So if we're really trying to drive a reaction forward in like an industrial production sense, then we're obviously going to want K to be above 1 as much as possible. So when you get an equilibrium constant like that 38,000 that we got there, then okay, good. That's probably a good sign. We want it to go forward as much as we possibly can. All right, so the K that we've been working on so far is the K for concentration, and that is pretty normal. We do a lot of that, but we can also find K using partial pressure. And so instead of just K, or instead of K sub C, which is concentration, we can use K sub P. And it works out the exact same way, except that you're going to plug in the partial pressure instead of the concentration. So partial pressure of ammonia raised to the 2nd power, Partial pressure of nitrogen raised to the 1 because it's got no coefficient, right? Partial pressure of hydrogen cubed because it had a coefficient of 3, and we will plug those things in and pretty simply crank out our math there. And you'll see that's the same basic setup, raised to the power of the coefficient, products over reactants. The only thing that's different is we're not using concentration, we're using partial pressures in this case. So let's just calculate one of these real quick, just to make sure that we can. And so our Kp in this case is going to be equal to, whoops, see I almost fooled myself there and did a little concentration thing there. Okay, so Kp is going to be equal to the partial, that should be an equal sign, the partial pressure of our NaCl, okay, and then that's going to be squared, because it's got a 2 here, right, over the partial pressure of NO, also squared because of its coefficient, and then Cl2. Okay, and so if we plug in our numbers here, we've got 1.2 squared over 0.05 squared times 0.3. Okay, and we plug all of that in, and we're going to get our answer of 1920. And again, just like our regular K, we don't have any units for this. Okay, so that what this allows us to do is that in a lot of cases, we're talking about gas phase equilibrium. And so we might not know the concentrations, we might not know, how big the container is, but if we know the partial pressure, we can then calculate the K value that we can still use for some equilibrium expressions. Now, what you might be asking yourself, is there a relationship between this Kp value and the Kc value? And I'm so glad you asked, because there is. Now, it's a pretty ugly equation, it looks like, but it's really not as hard as you might think. Your Kp value, okay, that's the equilibrium constant for pressures. K, that should be K sub C, okay, so it's a regular K. R is the same ideal gas constant that we've been using pretty much all along, and you're like, but we've used a couple, and that is true. So this is the 0.08206 liters, atmospheres, over Kelvin times moles, okay? And then temperature, of course, in Kelvin, and then that's raised to the power. The only hard part of this whole deal, let me switch my pen color here. The only hard part of this whole deal is this guy right here, the delta N. So delta N actually isn't as hard as it seems. It just means that you sum the coefficients of the products, which in our case, there was only one product, so it was 2. And then you subtract from that the sum of the coefficients of the reactants. So 2 plus 1 is 3. So that means that in our case, our delta N is 2 minus 3, so it's negative 1. And so if we wanted to calculate our K value for this one, since we already know our Kp was 1920. Okay, that's going to be equal to K times our ideal gas constant, all right, times temperature in Kelvin, 298, right, because it was 25 degrees, if you didn't remember that, hop back here, 25 degrees Celsius, so 298 Kelvin, and then raised to that delta N power, and we already established that that was negative 1 because it was 2 minus 3 in this case. And then, of course, then we just got to work out some algebra, which we're all good at this point, right? And so that gives us a K value of 46,951. And so what that means is that if we knew our partial pressures, then we could then calculate the concentration K value as well. And that might then allow us to actually calculate the concentrations themselves, which is what we'll do in the next video. Okay, so again, make sure you work through a few homework problems on this, or classwork problems, as the case may be, and ask some questions. We'll whiteboard some of these, and you guys, in fact, are going to actually record some of your own videos walking through these, and then we'll move on to the slightly harder problem of, hey, that's great, we can calculate K, but can we calculate concentration if we know the K? And the answer to that is yes, and that, of course, is sort of the heart of equilibrium chemistry. Thanks, guys.